The Taylor series provides a means to predict a function's value at one point in terms of the function value and its derivative at another point. In fact, any smooth function can be approximated as a polynomial using the Taylor series. A useful way to gain insight into how the Taylor series is beneficial towards numerical methods is to build it term by term. So therefore, if we have the first term, f of x at I plus 1 approximately equals the function value at f of xi, we call this the zero order approximation. And this indicates that the function at the next point, x of I plus 1, actually depends on the function value at the point xi. In other words, that they are the same. And from our intuition, this makes sense that if x of I plus 1 and xi are very close together, in other words, in a very small step size, that it is likely that the function value at the next step is going to be the same as the current value. This approximation is fine if our function value is constant, but what if it changes? If it changes, we can add additional terms to describe how it's changing. Is it increasing or decreasing? So we can add another term to the Taylor series, and that is that f at x I plus 1 equals f of xi plus f prime xi multiplied by x I plus 1 minus xi. That is the function value at our next time step is equal to the function value at the current time step plus some slope term multiplied by our step size. This change is linear, and we can add a second term and a third term to increase the accuracy of our Taylor series approximation. If we add all the terms, we can get an nth order approximation, and we know that the nth order Taylor series expansion is exact for an nth order polynomial. But this is not always the case, and for sinusoids and exponential functions, a finite number of terms does not equal an exact approximation. In fact, each term adds more accuracy, but only ever so slightly. And as an engineer, you are the one who's going to have to decide how accurate you want your solution to be. So how do you quantify how accurate you want your solution to be? Well, you can base this on our remainder function. That is, your remainder function at nth order for an nth order Taylor series expansion is equal to the function value n plus 1 of chi multiplied by x minus some constant a divided by n plus 1 factorial. Now we can define our accuracy based on our remainder term, but this remainder term has two drawbacks. And the first is that our chi value is not known. In fact, it lies between the value of x of I and x of I plus 1, but we don't know its exact value. Secondly, in order to evaluate Rn, we need to know the n plus 1 derivative of our function. But what's the point of a Taylor series approximation if we know the derivative of our function, because that would imply we know the function and we don't need our Taylor series approximation. So, despite this, we do know what our step size is, that is h or x minus a, and we know how Rn, our error term, scales with our step size. So if we have a zero order Taylor series approximation and we halve our step size, we know that our error term is going to scale linearly with our step size. So in effect, we've reduced our error by a half. However, if we have a first order Taylor series expansion or a error term of order 2, we reduce our step size by a half, we in fact have quartered our error value. Let's look at this further with an example.